Is my screen visible and am I audible?
Yes, yes.
So how was the last week's assignment? Everything, I mean, you were able to
Last week
solve?
assignment, last three questions, I could not get the good marks, but the 0 marks except
Okay.
first seven is okay.
What were the questions? I mean, on what was the topic of the questions?
Say again.
What was the topic of the
Say again.
questions? Sorry, I am telling. What was the
Topic
topic
of
of
the
the question?
question is that
Yeah. Hmm.
topic was that tracking control,
Okay.
whether it is marginally stable or not. So
Ah, okay.
that was the question.
So was it regarding getting some eigenvalues and all?
No, no, no. See, because I know whenever there is some resistive forces there,
Hmm.
system is always stable. So that means that vehicle which is shown
Hmm.
minus BV is the resistive
Oh,
force.
acha, acha.
Right? So
Yeah,
I
adaptive
thought
push control.
it will,
Okay. Hmm.
yes. So
Automatic
I
push
thought
control. Okay.
okay, because of that BB force, it will be
Okay.
always
Okay.
stable.
No,
So, but the
it
question
depends.
is
Depends.
marginally stable.
Depends on the matrix, right? How the state is changing.
No, no. So,
Depends on that.
can you see that assignment and last three questions if you can
Do you
five
have
minutes
it? Do you have it?
if
Can you share your screen with the
no, no,
questions?
I am having tab now, so I have to close and then open. That is the problem.
I don't know if I
I have
have.
logged in.
I am not logged into their portal, but can you send me the question? Do you have any screenshot or anything? Wait, I have to see. Uh, I am not enrolled to the course, I guess, so I will not get. Week 5.
Second, hello.
Week 5. Week 5, right? Hello.
No, no, five is okay. Last three questions.
Week
Yes,
5
yes.
assignment,
Five,
last
six,
three
seven. Yes,
questions, Trust, right? That is what. Okay, okay.
yes, yes, yes.
Let me check once. Okay. So basically, this week lecture was on hybrid automaton, right? So did you go through the hybrid automata lectures? Hello, or you can just type if you want. Hello. Okay. I'm guessing, yeah, you have gone through the lectures. So basically, I'll take you through the lectures and solve some questions like we always do. We do in every class. So yeah. So the first thing that we already know as part of our formal language course in computer science, we have studied finite automaton. So we know the definition of finite automaton. We know how it works. Obviously, here we are talking about. I mean here the description is of non-deterministic finite automaton. And why non-deterministic? Because it can take multiple different actions. All the possibilities will be simulated. So such an example is given for a vending machine. How a vending machine works, how should we write its code, if we can express that using an automaton, and what will be its initial states, considering that coin, coke, Pepsi taken, these are the alphabets. So these are the alphabets, and these as well mean I mean these are very expressive. You can understand by coin we mean we were inserting a coin, by coke we mean what do you want, and when we are inserting the coin, what is the product that we are asking for. So more products there are in vending machine, this alphabet will be elongated, and for this alphabet, these are the transition functions that you are getting. Transition functions meaning these are the rules that you are following while you are designing this automaton. They will be a map from a q cross alphabet set to 2 to the power q basically. So we'll get a set and an alphabet pair uh, from this state. With this alphabet we will go to which state. We can go to one state or multiple states, because basically we are mapping to a power set of the states. So with this description we can see that once we insert a coin, we ask for Coke or Pepsi, then the next action is taken, and when it's taken, basically I'm coming back to the final state and I'm done with what I desired to do. So this is a very basic description of a finite automaton. Is this understood? I think this is pretty standard and pretty straightforward. So what is important is this sample example run that we say, because we will be using something like this later frequently. So basically this is an example run in the automaton. Basically it's like a graph traversal. These are the nodes and these are the edges, and through the edges we are using some maybe the alphabets can be considered as some inputs that we are using while we are traveling from this state to another state. So this is how the language looks like. So this coin, Coke and taken is the language that these automata recognizes, right? It can be coin Pepsi taken or it can be coin Coke and taken, because starting from this initial state we are reaching to final state with this word. I hope these things are already, these just reminiscing the old things from computer science background. So yeah, here another example, garage counter example. Basically it's counting how many cars are there. I think yes, number of cars currently present in the garage. So if you notice here, the alphabets are a bit different, up and not down, down and not up. So this whole thing is in the alphabet. So whenever I'm giving something as an input from the alphabet, so this whole thing will come as an input, and eventually the count will increase. So as the count increases, hello, am I audible? Yeah.
Sir, I am actually on train, so that is why network is not correct. So you please carry on. I will see recording also. Okay.
Okay, fine, fine, fine. I'll just go through take you through the lectures. I think any part that you did not understand, just tell me that.
Yes, yes, yes.
Any part that you did not understand from the lecture?
Say again.
Any part that you did not understand
Sir,
from the
I
lecture?
understand, but no. See, problem is we I want some problems to be solved.
No, no.
Theory
Problem
understanding is
solving will
okay,
be
but till
done.
the time
I am telling problem solving will be done. That will do. But what I'm trying to understand, unless you understand the theory well, you will not be able to solve the
no,
problem
this
just by
hybrid automata is theory intensive.
Yes,
So till
yes.
the time I think that problem if we solve, then only theory will be clear.
Yeah, but yeah, it's like the chicken and egg problem. So yeah, I'll just take you through the lecture once, and whenever I come to some sorry. So I'll just take you through the lecture once, and then we'll solve some problems that I have made for this lecture. So yeah, this is very straightforward example, and regular language properties, I'm not going to those things because those are already known from computer science background. So need of hybrid automata is basically because finite automata that we just described cannot capture continuous dynamics. Basically they are capturing discrete dynamics. We are giving certain inputs from the alphabets, then based on that the state change is happening, like we have seen Mealy and Moore machines as well. So those are also examples of finite automatons, and they may have some outputs, they may have some inputs like that from the, they have separate alphabets. So those are basically discrete actions. So since we need to capture continuous dynamics of the plant, along with the discrete dynamics of the controller, we need to have hybrid automata to express such systems. And why do we need to express them as hybrid automatons? For verifying their properties, for verifying if they are working as desired. But we will come to that. We will understand what is verification and how do we do that using hybrid automaton and all. But before that, we need to understand hybrid automaton first. So yes, first example will be of a light switch modeling. So light switch modeling is nothing but state to state transition will happen based on if I press the switch and what happens based on that. So there are 3 states. I think light is off and will turn on if I press. So there is another action, if becomes brighter if we press the button for longer, or if we press the switch again within 3 seconds. So if you see this automaton, this is basically a finite automaton where the language only, the alphabet only has press as the alphabet. Alphabet set has the only alphabet press, and these are the states. So Q0 is the initial and final state. But you don't have the notion of time, because I need the notion of time here. So it is because it says if I am pressing the switch again within 3 seconds, so it will brighten up, right? So for that, what I can do is I can use a notion of time while I am second time pressing the press button. So here I can add one extra criteria based on which it will decide if it should get back to off, or it should brighten up. So we will see such examples eventually. So basically this is the tuple for an hybrid automaton, and this is not typically, all the elements are not typically same as the finite automaton, because this is very important. So there is a mapping to a vector field. So what do I mean when I say vector field? So basically this is a function where I am deciding from current state how the values will be changing, values of the variable, whatever variables I have. This is basically the space, state space or value space, continuous state variables. So here basically this function decides how these variables will change. It is similar to the change of functions in the continuous dynamic systems, like we write ODE equations, x dot equals to f of x. So yeah, an initial state is there. Obviously I will start from a state, and obviously I will start from a certain x values. I can only start from a certain region, I cannot start from anywhere in the state. Or if I start from anywhere in the state, so the whole state space is my valid initial region. Yeah, so invariant is something that should not change, that is something related to a particular state. So each state should have an invariant condition, so that condition should remain intact while I am in that particular state. Okay, so the mapping obviously will be from q to 2 to the power x. 2 to the power x meaning basically for all the variables I can choose any range of value from the set of valid state space. So this is something property of state. So when I am being in state, this should not be changing. So invariant q, this is how we write it. For a certain state q belongs to x, basically this is nothing but what are the values that are supported by this particular state when I am staying in that particular state. So here it might sound very confusing, so I will just denote q with locations instead of states, and x as set of state variables, basically space of state variables. So these are, this x is containing, if there are n state variables, x is containing each of their ranges. So it is an n dimensional space. So where for n number of state variables I have their ranges, and this is basically set of locations. I will not call them states anymore, unlike I do in finite automaton. So basically invariant will be I mean respective to each location, and they will be nothing but a subset of, it can be a proper subset as well, subset of a of the state space. So and yes, discrete transitions will be there. Set of discrete transitions are denoted with E. So basically from one state to another state I am transiting. So this is how the edges are defined, and there are guard condition, guard sets or guard conditions, however you call it. So basically these are mapped from these edges, basically q cross q to 2 to the power x. So basically when we are switching from one state to another, how should the state variables behave, or what are the values that the state variables should support at that time while I'm switching from one state to another state. So yeah, so this is also again a subset of X. So yeah, the reset map is something that I am getting when I am having I am at certain age and I am at certain value. So basically I can have any number of value mapping in that situation. So if I have a reset map at any age, basically whatever value I have currently, from that value I am mapping the particular variables to a set of values. So this is not continuous, this is basically a discrete, like turning on and off a switch. Basically I am resetting a particular set of variables to a new values when I am making a transition through an edge from a state to another state. So this is how these are the new elements in a hybrid automata, if you see. So the guard conditions, so the reset maps and the invariant conditions, right? So now using them, if you model the same characteristics of light switch, this is how it looks like. So if you notice here, so the discrete locations are basically q0, q1, q2, and the continuous variable x, only variable I am considering is x. So it's a one dimensional state space. Like when you are talking about that ACC model, we are in two dimensional state space. We are considering, I think, position and speed as two variables. So like that. So the flow dynamics looks like this, like we have also seen for the continuous time systems. So this is how it looks like, and it is initializing from q0 with a value of 0, value of which variable? X. So basically invariant q is denoted as x greater than equals to 0. Okay, so if you see in each of these states, this is the only condition on the state variable that I am imposing. So this must be hold. Okay, in order to if I want to stay in this state, this must be hold. So yeah, this is something. And edges, so if you see there are 1 2 3 4 discrete edges from one state to another, and each of these edges has one guard condition or guard set. So basically from q0 to q1, whenever I am going, I am having a guard set that is true. Maybe it is always true, it is not checking any condition, so that is why it's true. Yeah, when I am going from q1 to q2, I am checking if x is less than equals to 3. So this x is basically denoting the clock, I think. So whenever it is within the 3-second time gap, so when I am pressing again within 3-second time gap, then I am going to q2 where the light just brightens up. So yeah, from q1 to q0 again, when it x is less than 3, it is going then only, and q2 to q0 it's going always. So something like that. So q1 to q0, q1 to q0, I think it is written wrong here. It should be x greater than 3. Yeah, it is written correctly in the picture, I think. So it should be C. So from this state, if x is less than equals to 3, it goes here. If x is greater than 3, not equals to. Now if I am putting equality in both these conditions, it becomes non-deterministic, because when it is facing equality, it can go either to q2 or to q0. So this is deterministic pretty much. So it knows exactly based on the value of x where should it go. So reset maps, yes, reset maps are basically these values. Whenever I am going from q0 to q1, I am resetting x to 0 value. So basically I am starting the clock, it's like a stopwatch. Okay, So as I am going to this state, basically x dot equals to 1, this is what how I am changing based on time. For 1 unit of time I am changing x value of 1 x value, 1 unit of value for x. So yeah, this is the whole automaton now, and if you follow this automaton now, basically it is modeling that time sensitive characteristics of the light switch now. So if you notice here we don't have a final state, isn't it? So basically it can end anywhere. It is not like we have some acceptable words. So it is not about accepting certain words or accepting certain set of sequence of actions. It is about modeling the system, so it can be followed till anything. So it is not having any final state as in its tuple. That is why hybrid automata is not having any final state in its tuple. So it is modeling the system. Now with the model system, yeah, there are I think other examples of such modeling. I think these are pretty rigorous. If you go through them, questions will be coming from these modelings mostly. So because these are very rigorous, so just go through them very well. If you don't understand something, please let us know in the group, or you can write in the mail chain that I created. Anyways, so this is the description for the bouncing ball, how dynamics is changing. This is the dynamics. Now no, this is simple. X1 and X2 are the two variables. So X1 is basically the position and X2 is basically the velocity of the ball. So these are the two variables, and I know that when it's falling down, its acceleration, that is change in speed, x2 dot is basically minus g, because it is falling downwards. So with these equations we are trying to formulate an HA. So in this HA, if you notice that what is happening is I have only one state. I have two variables obviously, like we had here. So in this state, this is how the f, small f, that is defined. If you remember the tuple, hybrid automata tuple. So this is how it is defined. Along with that, this is the invariant condition, that it should be greater than or equals to 0, and it is only having a self loop, and how based on which condition it is going out of this state and again coming back. So the only condition it is having is x2, basically x1 should be 0 and x2 should be less than 0. So x1 is 0, meaning basically position is 0 I think, and x2 is less than 0, meaning basically velocity is negative, basically it is changing its direction. So when it's falling down to the ground and again going up, so at that time it is basically there is a self loop. So this self loop is denoting that, and there lies a if you check, there is a reset map here that we are using to, I think this is denoting something that I have not. The speed x2 is reset according to this, where c is a coefficient of restitution. So this is how I am transferring the velocity. So when I drop on the ground, I am losing some energy. So and when I am translating that energy to a velocity, so basically this is how it is changing. So you are updating x2 like this. Okay, basically x2 is changing direction, so negative c2. So and this is how it is being reset. So yes, this is how it works. This is modeling the a bouncing ball. For temperature control, I think it's a similar idea. I think the states are on and off. What are the criteria? I think these are pretty much understandable. I think if you follow the lecture, it will be understandable. Still, let me see if there is something challenging example. Leaking gas burner was something like within 10 seconds. The leakage is fixed within 10 seconds, and the minimum interval between two leakages is 50 seconds. Okay, so leaking and not leaking are the two. Yes, so basically what is it trying to do? So there are two states, leaking and not leaking. What I am trying to model, let's see what I am trying to model first, because whatever I am drawing, whenever I am drawing a hybrid automata, It is basically depending on the specifications that I give, or the model specification that I want to model of the system. I am not modeling the whole system, remember that. I am modeling a particular property, a particular characteristics of the system, because I want to verify something regarding that characteristics. So I cannot, if I model the whole system, obviously it will become a huge system. We'll see such a composition hybrid automata, we'll see. So for now, let's see how it is working. So it is basically trying to model, one wants to model and analyze the assumptions that whenever the gas burner leaks, the leakage is fixed within 10 seconds, and the minimum interval between two leakages is 50 seconds. So within 10 seconds, and the minimum interval between two leakages is 50 seconds. Okay, fine. If I am trying to model this, basically I need a clock variable that needs to keep count of the time, and leaking or not leaking. If it's fixed within 10 seconds, it is not leak, it will not leak anymore. If it's not, then it will continue leaking or something like that. It will be similar to something like that, I think. So yes, so there are two states here, leaking and not leaking. So I am entering with 3 resets. These are reset maps, if you see. So why 3 variables? What are they doing here? Let's see. So x is a 3D state space, because there are 3 variables, t, l and u. So this is how the leaking, in leaking state, the x variable changes. Okay, so x variable is what here? X variable is basically set of these 3 variables, vector. So this is how it looks like. Every all of them changes 1 unit in real time. As the time passes 1 unit, it changes by 1 unit. So this is how they change. And in non-leaking, basically the L variable is not updated. Okay, it is not changing, if you notice. Okay, so T and U are changing in the both states. In particular not leaking state, the variable L is not changing at all, if you notice. So initializing from the leaking state, I am having 0 values for all the variables. This is where I start from, initialize the system from. So now if I see the invariant conditions, how do I design them? I tell that in leaking state, U value should be less than equals to 10. And in yes, so that is the criteria. And ages are obviously from leaking to not leaking and not leaking to leaking, 2 ages, because there are only 2 states. So guard conditions from when transiting from leaking to not leaking, how are they changing? They are basically in the whole covering the whole state space. They can be in the anywhere in the state space. So but yes, when changing from not leaking to leaking, basically U should be greater than equals to 50. This is similar to the conditions that I just described here. So whenever it is stopping to leak, whenever it is fixed within 10 seconds, U is the keeping count of that time, and whenever it is beyond 50 seconds, basically it is leaking in. So yeah, so this is how reset map is again resetting the variable U, because I have to again start counting, right? Every time I am going to from non-leaking to leaking, basically I have to keep on counting. So every time I'm changing states, I am basically resetting U and I'm starting a countdown. Okay, so this is how the whole thing is modeled. Yes, this composition is what I was talking about. So we know how it works. We have seen some examples. Now HA composition. HA composition. So there are 2 hybrid automatons. IH, I am denoting each of the hybrid automaton with I equals to 1 and 2, H1 and H2. So H1 and H2 has different alphabets. I think alphabets are also different here. So all the things are different here. So how do I compose them together? If I want to find out an automaton that is a composition of these 2 automaton, how do I do that? Basically, we should see this through an example actually. So the flow condition, basically the alphabet will have all the variables, whatever variables we had. Okay, and yes, state space should be union. Okay, if I do union of the both the state spaces, basically it is considering all the states. Okay, and along with that, yes, flow equation should be followed for both flow equations should be followed, initial condition should be followed for both, invariant should be followed for both. Okay, so this is the new invariant initial condition if alphabet and state variable, state space variable for the new composition automaton. So if the following holds, then basically this is how the transition is happening from q1 q2. Now considering a tuple, this is how the changes are happening. So basically q is q1 cross q2, so obviously each of the state will be a tuple now, a state from q1 comma a state from q2. So basically this is how it looks like. So if I am transiting to q1 prime, q2 prime, with this, I think this is in alphabet. If any of the following holds, if this is in intersection of these two alphabets, then this can happen, and obviously these two edges exist in the actual hybrid automatons. So q1 to q1 prime, you can go in h1 using this sigma, and from q2 to q2 prime using this sigma you can transit in h2. So if they are existing, then only this is a valid transition in the composition hybrid automaton. So basically I am respecting, it is basically like getting intersection of two finite automatons. So if I consider two regular language sets, if there are two regular language sets, and among them if I do a intersection, basically the output is also regular, and for that if I try to draw an automaton, it will look like that only. So another thing is this criteria looks like that only. So what are the other criteria? Yes, so if there is a if this belongs to sigma 1 and not in sigma 2, I mean second alphabet of the second hybrid automaton, basically then obviously it will check if there is a transition in the first automaton or not, and the second state should be the same, because I am not changing states, because this alphabet does not belong to the second alphabet set of the second automaton at all. So same thing for the other condition also. And yes, and q1 q2 this is there. For this there will be guard conditions for each edge, and how will those guard conditions and reset maps look like. So guard condition will following both the guard conditions, so they will be ANDed. So conjunction of both guard sets or guard conditions. Reset maps will also be ANDed. Okay, if the alphabet exists in both. If alphabet is existing in only either of them, not both of them, then basically it should be following that particular automaton. That's it, as simple as that. So yeah, now there is a description of train gate controller execution 2 tank example. Okay, so so this is the train controller. I think this is for gate control. So train controller is basically having how many variables? Only one variable, as I can see, and in alphabet it has up and down, only one state variable, one dimensional space. So this is how it changes itself. It has a certain function. So it has two particular locations, train and left, and the names suggest what is happening in those particular, what are those particular states or locations, sorry, locations are signifying. So basically when y equals 0, when the train is there, then basically if it is up, then it is if there is an input, the alphabet from alphabet, if I am giving up as the input, so it is going to left state, and in that state y is having an invariant condition, like it should always lie within 5 to 15, and in train state it is always lying within 0 to 25. And yes, when it's 5, then only this is the guard condition. When it's 5, then only it is going there, and when it's 15 and there is a down input, then only it is coming here. Otherwise it is having a self loop in train when y is 25 and y is reset then. Okay, this is how it works. So this is nothing but when the train is leaving, basically I am now that the gate automaton is basically, this is basically signifying when is the train coming and when is it leaving, and this is basically signifying when the gate is down and when the gate is up. So lower and raise are the two states obviously. So x dot is changing like this, x is changing like this, and in each of the states, and when it's up it's raising, it's in the raise state, when it's down it's in the lower state, and it is starting with x equals to 1 value. So let's see how we are composing them now. So while composing them, this is what is happening, the composite automaton. So basically how many variables? Again, I think one variable is sufficient. One variable. So resetting that variable and starting. So q0, q1, q2, 3 states in this case. So for the first state, I am changing the value of x as x dot equals to 1, and for the second state I am changing, for all the states I am changing it like that, and yeah, for the first state it should be greater than equals to 0, and the second state it should be again the same, because q0, q1 and q2. So basically how many states should be there? Basically there should be 4 states, because I am making a composition composite automaton. So train comma lower, train comma raise, left comma lower, left comma raise, these are the 4 states. Among them I think one state is unreachable, so only 3 states are left. And if you follow the rules that are given, then you will find out that this is the automaton that you will get. So this is a 3-state automaton that you are getting. One state is unreachable, one state will be unreachable. If you follow each of the guard conditions and if you add them in each of the edges, this is how you get the composite automaton. And there is a 2-tank example, I think that is for, hold on, execution of HA. Yes, so this is important because this is something that we will be using later while we will be verifying each of the runs of the hybrid automaton or each runs of the physical system. So a hybrid automaton is time trajectory, we call it. Time trajectory is a collection of consecutive real intervals. So basically now we are changing states through some intervals, right? So with the change of intervals we are changing states, and this change in states are happening expressed like this. So formally this is a sequence. So each I1, I2, these are basically intervals. So these intervals are denoting what? This is basically denoting how long they are staying where and at which interval they are changing states. So if we see an example here, execution. So execution of that hybrid automaton is a collection X, where this is a time trajectory like this. So time trajectory looks like this. It's just different time intervals. Now each of the time intervals we are defining a prefix for each of them. So said to be a prefix if denoted as this. So basically this is a prefix if its length is less than equals to its actual length. Okay, so index set is basically how many intervals are there, as many intervals are changing, and length is basically their summation of their lengths, I guess. So yes, with that we have the execution semantics for the hybrid automaton with what? So basically these are the time trajectories. Along with that, this is the mapping, providing locations for each interval. So my objective was to understand how it is traversing through the hybrid automaton, right? This is the idea of understanding an execution of hybrid automaton. So execution semantics is basically Q is something that is mapping these time trajectories to locations. Okay, so X is basically a collection of differentiable maps. Okay, so differentiable maps, that is like from intervals it is mapping to certain variables. So basically values, every time you are changing, you are going forward, you are changing different going through different time intervals, how your values of state variables are changing. So it is combining time intervals along with what are the locations that you are being in, along with what are the values of the state variables that you are attaining at those time intervals. So this is a collective definition of execution of timed automaton. So if I go to the two tank example, I think these are all explained very well. So this is the two tank hybrid automaton. So I think I'll just go through the rest of the slide. If there is something important, then I'll just go to the tutorial straight away. So some more notions. So non-blocking and deterministic hybrid automaton, yes, these things are important. So basically execution prefix is an idea, basically execution maximal when basically prefix is something when you are defining prefix, basically x is considered a prefix of x hat. In this case, this is how it is defined. So it is denoted as this. So when I am saying I am using a new notation to denote that x is a prefix of x hat. So this is true only if t is a prefix of t hat, t prime. So t is in x and t prime is in x hat. So for all I belongs to t, obviously this time interval that I am considering, this time trajectory, sorry, not time interval, for any interval in the time trajectory, for all time in that particular interval, if you are getting qi comma xi at ith time instance equals to q hat I comma x hat I. So this basically denotes, basically at that particular time instance, if both are suggesting for you to be at the same state and at the same valuations of the state variables. Okay, so if they are not equal, if they can be equal as well as of less length, so if they are not equal, x is basically a strict prefix. Like the idea is similar to having a subset and a proper subset. So like that only. So execution is maximal if it is not a strict prefix for any other execution. So these are the properties. I think these are very well explained. Yes, this Zeno criteria is basically is very important, because this is something that we have to avoid while we are modeling the hybrid automaton. So Zeno, if it is infinite, but this is less than the time interval is less than infinity. Uh, that means basically within a finite total time duration, if I am changing infinite states in infinitely, then it is a Zeno phenomenon. Basically we call discrete transitions are happening multiple times, where more than I expect within a finite amount of time. So it is repeatedly changing states. So there is some problem in my modeling, so it should not be having such modeling. A few more notations, I think. These are basically notations that we'll be using later in going forward in other lectures. We'll be using these notations to denote that executions of hybrid automatons starting from q0 and valuation x0. So this is basically, obviously we know how it gets initialized. So if it is initializing from this INIT, basically this is how we are denoting the execution of the hybrid automata H. So when I am telling that using an M prefix here, basically this we are calling this maximal executions with this, and star is basically all finite executions, infinite basically all infinite executions. So as simple as that. So blocking and non-blocking, this is important actually. So a hybrid automaton H is non-blocking if this infinite execution is not fine. So basically it can carry on for infinite amount of time if its criteria or guard conditions or the invariants are not written as such. It will stop it from running infinitely. So most of the systems, maybe when I'm using my router at my home, or many systems, most of the systems that we run for very long, they will be having certain they will be a they will be modeled by a non-blocking hybrid automaton basically. So yeah, and hybrid automaton is deterministic. When it is deterministic, when it is basically contains at most one solution for all initial conditions. So basically this maximal run, when this maximal execution trace is having one solution for each of the initial states. So from each initial state I know there will be definitely one possibility. So that is a deterministic hybrid automaton. Okay, so based on the initial situation I am changing how should I execute the automaton, and they are not overlapping, there is no non-determinism here. So then only it will be called deterministic hybrid automaton. So yeah, so with this I'll move on to tutorial. So there are certain this is something that you often get in your assignments. I think this I'll do later. I'll start with this problem. So if you see, these are hybrid automaton. Okay, so this hybrid automaton, any questions in the lecture? I'm just I have spoken for so long, I just need a feedback. Anything? I mean, I hope I took you through the lecture material. I hope it was somewhat understandable. If you go through the lecture again, you will understand. So the questions will be mostly regarding, hello, am I audible?
Yes, yes. Can you explain this number, question number 3? How we have done this?
Yes, I'm about to.
Question 3, please explain how to calculate this.
Did you understand this hybrid automata? Do you understand the hybrid
Yes,
automata?
yes, but still,
Can
how
you
to
explain?
go about
Can
it?
you explain what are the variables here?
So
State
here
variables,
variables are state variables are X, Y, and
right?
L.
Right. Not L. L is basically the state, location. Sorry, L is, so there are 4 locations if you see, right? L0 to L3. So these are not variables. So these are locations. And what are the guard conditions? Which ones are the guard conditions? I'm just trying to understand if you are familiar with the idea of the hybrid automaton. Then I can move forward to solving
The
the
guard
question.
condition, which is in between the two state, what I understand.
Yes, yes, you are right. So invariant conditions will be attached to every location, and the guard condition or the guard sets, however you call it, they will be attached to every edges between the locations. And along with guard condition, we have reset maps. So you can see here a reset maps, guard conditions, all are there, all are present. So these are logical, obviously. These are not assignment operators, these logical operator and these assignment operator. So anyways, so the question here is following the notations that we learned in this course. So what does this denote? And this denotes. So basically when I say GL2 L3, what does this denote basically? Hello, am I audible? Hello,
Yes, yes, audible, audible,
I am asking, when I'm saying
audible,
what is the
audible.
guard condition when I'm switching between L2 and L3, which one should you denote? I mean, which one should you, I mean, point? What is, which one is the guard
X
condition
is equal
from,
to 0. X is equal to 0.
right? X not equals to 0. Basically, this is basically resetting X to 0, right? X reset to 0. So this is the guard, this is a reset map. This is not the guard condition. So you are telling the reset map from L2 to L3 for X. The reset map is this. This is not the guard condition. Which one is the guard condition? This is the guard condition, right? So this is nothing difficult. Using this, what can we solve? So for this hybrid automaton, what should be the state when y equals to 10 and x equals to 3, right? Now if we start simulating it, I am starting from y equals to 1, right? And y is changing how? Here y is changing one amount every unit amount of time, right? So if I am entering with y equals to 1, then y is changing like this, and I stay in the state L0 as long as y is less than equals to 10, right? So at the values, when these are the valuations of these particular two particular variables y and x, where should I be, at which state should I be, and what are the valuations I have already told you. So which state will I be? What do you think? How do we solve this? If we start from here, we are changing by 1. So when should I switch the from L0 to L1? When should I switch? I can switch when x equals to 0, 10, sorry, y equals to 10, and I will reset x to 0 while I am doing so. So at y equals to 10, my x is also changing with values, 1 unit of values every for every time unit. So basically x and y are changing equally here, right, in this L0 state. So in this state, both of them will reach 10 value after 10 amount of time. So when y is reaching 10, I am switching the state to L1, and x is having a value 10, right? Because both of them are changing equally. Is it understandable what I'm telling?
Yes.
Fine. So now I am at L1. Now what is going to happen at L1? I am how am I changing again? Now see, x is having a value of 0 and y is having a value of 10 here, right? So as long as x is less than equals to 2, I am allowed to stay here. When x is equals to 2, I have to change the state. So when I reach 2, x equals to 2, I will reach y equals to how much? What will the y value? Hello?
Y is equal to 2 because y is equal to 12.
Yes. So with that value, I will be changing state again, right, at that particular time, and I am not resetting anything. So those variables are having their values as they used to as they were having. So I am at L2 state now. Now x is still changing with this in the same rate, but y is changing in a different rate, and it's reducing 2 units every time at every time step. So at y equals to 5, I will change the state to L3. So it can only stay in this state as long as y is greater than equals to 5. So tell me, by the time y becomes 5, what is the value of x? I am entering here with y equals to 12. By the time y becomes 5, what is the value of x? And I am entering with x equals to 2. So from 12, it will take how many time steps to reach 5? Hello? Is this understandable? I'm trying to understand if you are
Understood.
following.
Understood, sir.
Okay, fine. So basically, it will take, I think, 3 time steps, I think. So after actually, I I am interested in when y equals to 10 and x equals to 3. Basically, here it will reach after 3 time steps, x will become, I guess, 5, and y will become, I guess, 6, below 6 when it goes below 6. By that time, I think x becomes 6 also, and it will move on to L3. But I am not going to that, because what I want is when y equals to 10 and x equals to 3. So by the time y becomes 10, so it is entering with 12. In the next time step only it will become 10, and by that time x will become 3, right? So I am reaching this particular valuation that I am asking. So at that time I will be in L2, right? So that will be the answer. It is as simple as that. Is this understandable?
Yes, yes.
Great. So these are the most these are the most involvement types of questions that you will get. Others will be mostly on the properties of hybrid automata, because this chapter is mostly full of theory. So Zeno phenomenon is a hybrid automata that happens when there exists a prefix x of x hat such that n equals to what, and so can you tell from the definition of prefix what should it be like? So what is xenophenomenon? Xenophenomenon is basically within a finite amount of time when I am having infinite number of discrete transitions, right? So when xenophenomenon is on an HA happening, when there is a prefix like this of x hat is a run basically such that n equals to this, and n is the upper bound of the switching index I for the runs in x. So switching index, I can switch up to n index. So when I am denoting this, basically I can switch infinite times, right? When xenophenomenon is happening, what I am doing is within finite amount of time. So this is my time trajectory, right? Time trajectory length should be less than infinity. So it is finite. Within finite time, I am having infinite number of discrete transitions. I am switching between infinite number of indexes, discrete time indexes. So this will be finite, infinite, and this will also be infinite. So then only I will figure out that within finite amount of time, I am switching infinite amount of I am having infinite amount of discrete switchings, and that is what we denote with xenophenomenon. And this is something we try to avoid while we model hybrid automaton. So is this understandable what I'm trying to say?
Yes.
Great. uh, Now this is something, the composite HA must have all the, so among this, which are the false statements when I am composing two or more hybrid automatons. So the composite HA must have all the continuous variables of each of the HA and that are to be merged. So and the composite HA should abide by the invariants of each of the HAs that are to be merged. So it is saying the composite HA must have all the continuous variables of each of the HAs that are to be merged. So I am trying to find out what are the what are the false statements. Yeah, this is obviously true because I need to have all the continuous variables, right? And this is also obviously true. I need to abide by invariants of both because I'm compositing both of them, right? And this is like composite HA must have trajectories similar either of the trajectories of the HAs that are to be. This is partially true. This is not always true because it might not have a trajectory that is similar to the trajectories of HAs because the states will change, locations will change. Locations are now pairs in composite hybrid automaton, right? So the trajectories will only resemble if they are having a common alphabet. Then the transition that I am having in that composite or hybrid automaton will be exactly following the transitions of in the those particular hybrid automatons. If the alphabet that I am using that is in either of the hybrid automatons, then it will exactly follow that particular hybrid automaton. So when I am not having a common alphabet that is in the alphabet of both the hybrid automatons, then basically this is true, but this is not totally true. So this is false, I think. I think this should be true also. Then initial state for the composite HA must lie in the intersection of HAs that are to be merged. Definitely, definitely. When both of the initial conditions are abided, then only the composite automaton will initialize. So is this understandable that this is, I think, wrong? Yes, this also says like that. So this is understandable. Why is this wrong? Hello, hello. Am I audible?
Yes, yes,
Yes. This is understandable what I just explained. Why is this wrong?
yes,
So basically, what continuous variables in HA? What do they help us to model? So what should be the answer? Basically, this is a descriptive question. So these all things are basically modeled using continuous variables. So we'll be unable to model either of them. So this tells us the importance of using continuous variables in the hybrid automaton. So system, how it is changing with time, how an event can be invoked changes. It can invoke changes in the certain system states, because we are doing that based on the continuous time, right? How does the system behave when it is in certain discrete mode of operation? So we are not able to describe the, by valuations of the particular continuous variables only, we are describing how the system is behaving. When should a system switch to different characteristics flow, or in order to cope with the current change in the system? So this change is also in guard conditions when we are deciding how it should change and everything. That is also depending on the continuous variables only. So everything is all the things that I am saying here could not will not be we cannot model these properties if we don't have any continuous variables in the automaton. So this is something the matching question. So an assignment on the continuous variables while the HA is transitioning from one state to another. So what is this? And assignment on the continuous variables while HA is transitioning from one state to another. What should it be? Hello. There is an element of the hybrid automata tuple. Which one is it? Am I audible? Hello. Hello.
yes, yes.
So can you identify which one does this denote? An assignment on the continuous variables while I am changing states, locations, transitioning from one location to another. So this is basically a reset map, right? That is the only assignment that I do while I'm changing locations. And vector fields, assign a vector field to each of the locations. Different location, different vector fields. Vector field means how the continuous variables are changing. So this is basically flow dynamics of the hybrid automaton, and collection of some conditions on the continuous variables in hybrid automaton that decide whether a transition from one location to another location should happen or not. So that is basically guard conditions. So using these only, they are the elements of the hybrid automaton. So somewhat this is mostly theoretical. So somewhat the idea is clear now, what is what and why we are using this, and the definitions and everything, what kind of questions can come. Hello. So yeah, I think I have gone through the tutorial. So I'll upload this. You try to solve this by yourself. I think it is pretty straightforward. This chapter does not have anything much, but these theoretical things are very important. Going forward, we'll be using them. So try to get the gist of them and understand them. So I'll end my session here today. Any questions that you have? Any part of the lecture that you did not understand while I'm taking you through the lectures? Please tell now, or I'll end the meeting here. Hello.
If x is the state, then if q is the state, then x dot is also dependent on q. That is true or not true?
Sorry.
If q is the state and then x dot is equal to q, that is dependent or not?
uh,
There is one question.
what is
uh,
x dot? No, see, I am not here to help you solve the assignments. I cannot answer your assignment questions, that is illegal basically. But what I can help you understand is what is x dot. What is x dot in this definition? What is x dot?
So in this definition,
Hello, in this definition, what is x dot? X dot is basically the flow dynamics or the vector field, right? F. So if you see the definition of vector field, it takes maps from q cross x to r to the power n. So you can see it is obviously depending on a state. This is basically we are see. Let's make a habit of calling q as a location set of locations here, because set if we say state, then they are state variables, or you can call them state and you can call x as state variables. Either way you can call them, but what I'm trying to say is this is the map that f follows, x dot follows. So seeing this map, what do you think? It should depend on the location or the state or not?
yes, yes,
So so
now
it is
clear.
very
Okay.
evident. It is very evident. Just read the descriptions very well. Then it is very easy to understand what is happening and what is not. Appreciate the idea, then it will be very easy to understand. It is not always about solving the problems. Yes, it is about solving the problems, definitely, but there is a greater purpose there. So for this slide lecture, actually there are not much problems that you can solve, but you can understand how to model them, because we will be using them later in the next lecture maybe. So I hope, do you have any other questions? Hello. If not, then I'll
Yes,
be
sir. Thank you, sir. Thank you.
okay.
Clear,
Okay.
clear,
Okay.
clear. Thank
Try
you,
to
sir.
solve. I'll upload these problems. Try to solve them. I think it will be easier for you. Okay. Bye then.